Today I'm going to talk about firmware verification using secure elements and the TrustFlex variants of our secure element. We'll go through, where do we see that being used in the market, and we're going to end up talking about transaction diagram at the end of the session. So without further ado, let me dive into the topic. And when we look at embedded security, right, we look at hardware without trust, counterfeit protection, IP protection, secure update, secure connectivity, and application layer security. Above that, there are other practices that need to take place, and that goes beyond, but that start to go beyond the embedded side of things. At Microchip, we offer a variety of solutions for microcontroller, 81632 microprocessor, secure element network controllers, whether they are wired or wireless solutions, and a series of FPGA solutions to address all of those use cases. Today, I'm going to focus on solely secure elements and the firmware verification use case. So how does it help with? There are a couple of, we take some big items. It's brand protection, preserve the quality of your product, or you avoid counterfeit. You avoid lower quality and lower performance of your system. What this is really saying is you're protecting the user experience. You're preserving the user experience. You can also have control accessory strategy. From a revenue stream standpoint, you protect your revenue stream by avoiding those counterfeits, right? By also protecting your user experience, you make sure your user keep consuming your product and they stay happy with it, right? And then the third bullet point, we'll talk about enabling a new service, a new revenue stream by the service. Something we've seen companies using our technology for is because you can authenticate, a replacement part, for example, in an elevator. Well, the company buying the elevator will also need to call the maintenance service of the original provider. That's something we've seen happening in the industry. And obviously, you want to reduce cost. There's a lot of cost involved into legal actions and warranties and stuff like that you could reduce/mitigate by using this type of firmware verification practices. So what is the IP protection? Really, the value in the value of your product is really in the intellectual property. It's your IP, right? So the value is in your code. The hardware has been tremendously commoditized right in the past decades. There's nothing new there. So what you want to do with your code, you want to sign it and verify it later in time. So when does this sign and verification happen is what we're going to see. A couple of more concrete examples are, drones. There's nothing connected to the internet in most of the cases there, but the core of the value is in the code that runs the drone. An air dryer, as simple as that. You can go from an air dryer now to military equipment or stadium speakers. That's where you can see the value of the code in all this application. We see that over and over and over. So how does it work? Like I said, you have a code that you need to sign into a secure environment during your manufacturing. You want to load the signed code during your manufacturing into your controller, whether it's an FPGA, a microcontroller, microprocessor, and you want to verify the signed code with the associated key at any relevant time. And I'll mean what any relevant time means. So at Microchip, we have several options that we offer to the market depending on your decision for the core, if it's a microcontroller, processor, or FPGA. So when we see, I'm going to focus on the branch here that use a standard traditional microcontroller. Doesn't necessarily have IP protection, so basically have something in that could do a verify function. So that's where the secure element comes as a companion device to achieve that. We have other devices like our SAML11 Trust Zone microcontroller, the SAM-A5 also equipped with Trust Zone, PolarFires that have trust execution environments. They have all the capability. And you don't need a secure element with those parts. When the IP protection is not in place as a feature in your core, secure element takes its importance there. So as we talked about, there's a key that's going to be used to sign, a key that's going to be used to verify. So one of the foundations of security is all about the key. We're pushing the concept to the extreme there, but it is at the root of every security system here. So we have Kirchhoff here that tells us that the crypto system should be secure if everything about the system except the key is public knowledge. And on the other hand, we have Claude Shannon that tells you the enemy knows the system, so you really want to protect your key. That's the lesson here. Why keys are important? Because with the possession of the key, you can impersonate critical transaction, and that's what you want to avoid by any means. So how do we protect the key into a system, especially a system using a core that doesn't have those crypto capability, that verification capability of the code? That's where the secure element comes in as a companion, as an elegant companion device that can help you scale your architecture, because you keep your microcontroller standard, traditional, and you just have that little add-on that gives you those features that you've been missing. So it's basically some type of vault that sits as a companion device next to the microcontroller. That's where your keys is going to be. And really the philosophy is the microcontroller here on the left side uses something called CryptoSlib. It's the library that will have all the necessary API to talk to the secure element and create a challenge response implementation. So the challenge will be sent to the secure element that will use its crypto engine depending on the crypto required here for the given use case. It will also state the key to create a response that will be validated on the host level. The host could be, again, a microcontroller, processor, FPGA, or cloud platform itself. The interface could be single-layer as QWERTY. And the idea is to make sure the keys are not exposed during the development and the manufacturing phases, and certainly not when the device is deployed. And you keep those keys completely isolated from software, people, manufacturing, and I forgot the last four. Sorry. So what's a secure element look like inside? You basically have hardware accelerators, hardware crypto accelerators, should I say. It could be an elliptical curve, RSA, AES, all those type of algorithm. You have a security PROM, you have a unique serial number, monotonic counters, and a high-quality random number generator. That's really where the high value of secure element is those high-quality random number generator will contribute immensely to help the generation of your keys and ensuring for the system fixed level certification when it's needed. So the challenge with this, with security as a whole, it's not with security, but as security as a whole, is you have a notion of personalization. Because what you do in security, you should have a unique key for each product. Now that means each of the code in each of the products you're manufacturing is going to be unique. That is a supply chain problem, right? How do we handle security, complexity, and customization during product development and supply chain is what we're going to talk about, is how we see how Microchip addresses that. So think about that notion of, now we're going a little bit beyond security. We're talking about the problem of customization to implement, because we're implementing security practices that will involve key, no matter what. The keys will always be there. And how do we mass produce this system? So Microchip has launched, we've presented that quite a few times already. The Shields Up #2 goes in detail on that session. Microchip launched the Trust platform for the crypto authentication family. That's composed of a 3-tier Trust and Go, Trust Flex, and Trust Custom. Trust and Go is basically a black box system that when you buy a device supported by the Trust and Go platform, you also get the keys by default when you buy the device. So it's pre-provisioned. We can deliver shipment down to 10 units for minimum orderable quantity. Moving up a notch, the Trust and Go, what it does device to network authentication, whether it's a TLS network or LoRa network. If you want more than that, the Trust Flex offers the same thing, except we don't lock the device this time, because we will allow customers to change the default credentials we position by their chain of certificate, for example, and have much more use cases. And I'm going to dive into that in a minute. The MOQ here, including provisioning, is 2,000 units. And the Trust Custom, it's basically a fully customizable secure element that we offer an MOQ, minimum orderable quantity of 4,000 units. All of them come with a GIL high rating. That's how we evaluate, that's the grade we get from the third-party labs we use when testing the capability of security storage for devices. As you can see, the Trust Platform program is not limited to the 8608. We have also applied it to the SHA-204, and we're going to continue to apply that program to upcoming products. So the Trust Flex is what we want to dive into today, because that's where we've implemented default use cases. So one of the struggle in the market was to figure out what use cases the client wants, how to implement it, and now you get into configuring your secure element. The way we configure those secure elements, we've actually done it for the clients. And here's the list of, it's not a complete list, but it highlights most of the key use cases TrustFlex is capable of supporting. The one that's going to interest us today is firmware IP protection. So as you can see, TrustFlex can do much more than that. It's not one or the other. It's all of it at the same time if you wish to leverage all of those use cases at the same time. And the only thing that will be needed from the client is really getting into the secret exchange that the TrustFlex device can receive the symmetric secrets, for example, the certificate. So then the next phase after that is getting to a secret exchange. So what are the...
Xavier, really quick,
yeah.
sorry to interrupt. We do have a couple of questions that have come in. First being, what is the difference between high-quality RNG and TRNF?
Marketing. Marketing. So if you look at the spec, the high quality, you're talking about pseudo random number generator. When you hear, that's what it was taught to me. True random number generator. If you look a spec, I don't think there's a spec per se, technical spec that per se that would call for a true random number generator. I think there's a bit of marketing behind true random number generator. Pseudo random number generators is the technical term you want. High quality random number generator is another one. Nothing is true or perfect in security, right? So I think that the actual technical term is pseudo random number generator. Was there another question, Megan? Okay.
Yeah, and I know you talked about all the features of the TrustFlex ATCC 608. How does the TrustFlex help clients?
Yeah, so that's the point. Those are features of the TrustFlex. So how does it help the clients? Is actually in my next slide. It brings flexibility, reduce time to market, make sure the tech is available to the mass market, which is very fragmented, and it simplifies the support. So from a flexibility standpoint, what it does is it supports any core, any cloud, any certificate authority, multiple use cases, and everything is baked in. And that's where it leads me to the next point, time to market. We've tried to reduce the time to market by offering predefined use cases inside TrustFlex to avoid our clients to spend time, or those use cases are the ones that we've seen being used the most in the past several years, so we decided to implement them for the client. But yet we keep the secure element completely configurable with the Trust Custom format if the clients don't have enough use cases or the use case is not present in the config we offer. Availability, right, that's a big hurdle in the secure element industry, I'd say. You see at the market, generally, to get the direct support, anything below 100,000 units it's not going to be looked at to provide provisioning. What Microchip has done, we've lowered the bar down to, have you seen, 10 units for Trust and Go, 2,000 for Flex, and 4,000 for Custom. And support, because we pre-configured the use cases ahead of time, obviously, the support structure is less intensive and is more intuitive. At least that's what we hope for. We also deliver something called the Trust Platform Design Suite that removes friction. So the design suite reflects those use cases. It helps with the onboarding of the secret exchange. Again, the idea is to fast track the time to market for clients. So let's dive into the secure download firmware updates, and we're going to get a little bit more technical, talk about transactions here. First, let's define it. I know the description of the decision was also including Secure Boot. Secure Boot will be differentiation. So we talk about firmware verification, which was the title of the session. There are really three things. You verify, when do you verify your firmware? You verify it after an over-the-air update, for example. You can verify it during runtime, and you can verify it after boot. That's the notion of secure boot. So secure boot will be an entire different session. We have it scheduled in the Shields Up webinar. I think it's worth its own 30 minutes. Right now, we're going to focus on the secure download firmware update, which is basically another word for OTA. But the practice are almost the same. They are the same at the secure element level. There are some slight variances in how you execute the code from the microcontroller. So let's get into the first example we have. Is showing asymmetric secure download firmware upgrade. There are two phases. And then the next case we're going to talk about is symmetric secure DFU. The first phase is for asymmetric is what's happening at the client side, at the customer side. So that's the signing process, basically. So you have an application image that's going to be hashed, and a digest is going to be created there. The customer ideally would want to use an HSM because you're going to start dealing with your private key, the client's private key. We've seen various practices. HSM would be best practices. We've seen other variances of that basically lower the security bar, but it's happening. So what really is happening there at the customer side, you have that sign operation. An asymmetric code will have an ECDSS sign operation. And out of the private key, public key is generated, right? And that public key here is going to be the one that's going to have to verify the code later. So how do you pass this public key to your let's call it that IoT system now? Well, that's what we're going to see in the next slide. To create a signature, we create a sign operation that outputs signature, and in the payload that you're going to issue to the system, you're going to have and the signature that's the output of the sign operation and the image, right? We make a big assumption here. We have not talked about encrypting the firmware. So here we're assuming the firmware is in the clear. Again, not really a best practice, but we're trying to simplify the diagram for now to focus on the sign verify operation. Now you have your payload that has the image and the signature, and we'll also have the public key and the certificate. What's coming next, we're going to update that code to the connected device, and that's the next slide. So the flow that we picked up there is going to enter here. We have this code that's being pushed that has, again, your application image, the signature, the public key, and the certificate itself. Now, what's happening with this payload, now the install system is basically where you have your microcontroller and your secure element is sitting next to it. Imagine this is your IoT device, and that's what we're saying here in the title. It's inside the deployed IoT device, what's happening. So in your microcontroller, you're going to have your code, and secure element, you're going to have something that happened. That something that happened is your ECDSA verify. So now what we've done, we take the public key that will verify the code that was, I'm going back to the last slide, that was signed during the manufacturing. This is it. So it's basically a simple sign verify with a public-private key pair. If the verification is successful, basically the new code is being pushed into the microcontroller. And before it does that, the signature of the image itself will have another another verify operation. This time, again using the manufacturer public key that will help to verify the hash of the digest. So meaning the hashed code here is going to be allowed to execute, and that's where we reject or accept the code to be updated after the over-the-air update. Now, we were in the asymmetric world. We're going to move to the symmetric world, which there's also a way to do that. And really, what you have here, it's a hash function. It's a hash function with MAC and checkmarks. So here's your code that you're going to have to hash, and this is happening at the customer site, right, at your manufacturing plant. That has nothing yet to do with the embedded system. It's actually not a secure element here. I have a typo. It will be more of the secure element could be used, but let's use the word HSM here. Once the hash is done, the output is a MAC, and now in the payload you're going to have your you're going to have the application image and the MAC, and then we're going to push that payload to the embedded system. Again, we make the same assumption that the code that gets here is nuclear, and you can encrypt the code if you desire to, which will be part of best practices. So once you move into the actual IoT device, where your microcontroller and your secure elements are, right? Well, that's where we find our payload. From the payload, we're going to take the image will be pushed through a hash with the parent key that was used here to with the first hash. Once that's done, we will produce the MAC, and that's where we use that check MAC function that I was mentioning before, where we have the MAC that was issued from the customer side, the customer manufacturing side. We get that reproduced MAC, reproduced within the embedded deployed system. That's the deployed IoT system. We run the check MAC, and the comparison of the two should be equal to make sure you can allow your firmware to work. And now only then you can push your application image. So if you can see it, the concept is pretty simple. The question for firmware verification, 3 use case that I've talked about is, when do you do that? After to boot your system during runtime or after an OTA? You can use symmetric or asymmetric. Asymmetric tend to become more of a best practice because you use the concept of public key infrastructure there. That's a little bit easier to manage than symmetric keys, and offers, I'd argue, somewhat of a more manageable key ecosystem. So how do we develop this whole thing? What Microchip offers there? We start with this DM320118. It's the Trust Platform USB kit. So you have a USB port that you plug to your laptop. You have a Cortex M0. And you have the 3 variants of Trust Tango, Trust Flex, Trust Custom that you can select with switches. And that's your starting point. If you want more of our secure elements, we have this micro bus port that allows you to have add-on boards. You could have more secure elements. We have more of the Trust and Go Trust Flexes here, and Trust Custom. If you're locking your Trust Flex, for example, mistakenly, this offers you a bit more options and trials by using this add-on board. That's pretty much all you need. This one is just enough for now. If you want to go a step further, we also offer socketed board. Actually, it's a partner company, Micro.com, that offers the socketed boards where you can have your standalone devices on that socket on that board here. And for those who are familiar with our Explain Pro form factor, that's the form factor of the bus here. We also have socketed versions for that. So that's your hardware. From a software standpoint, I mentioned the Trust Platform Design Suite, and what it is software that would basically help you to select the use case that you want, one by one or multiple use cases at the same time. It'll basically drop the configuration visually, and that's kind of what the configuration looks like. Once you're in that environment, the first thing you're going to do is you're going to work with Python executable tutorials to implement your use case. So you have the whole use case coded in Python. It's going to help you to not only operate the use case, but also create prototyped credentials, whether they're public keys, symmetric keys, private keys, and take care of the provisioning for the sake of that thing. You don't want to use that in production. Let's be clear with it. Once you've proved your use case is working between your laptop and your secure element, we also offer the equivalent C code example within that Trust Platform Design Suite to implement that exact same use case. And the last thing we offer is a utility that will help to trigger the secret exchange that you need for the Trust Flex offering here. If you go to this hyperlink here, we have that's where you'll find the installation manual. If you go to any of our web pages, they will all guide you to that tool. So it's not like it's hidden in the web. I'll show you in a minute if we have time where to get to it. So you have your hardware, you have your software development environments, And I'll conclude there. Hopefully, I'll take the last minute to show you where to get the software. What we've tried to do is to make everybody's life easier, reduce time, and reduce the complexity. By offering predefined use cases, a simpler tool set with a software design suite that you don't have to go and search for a given code example. We put everything at the same place. The flow helps is pretty powerful because it leverages e-commerce stores, whether it's microchip purchasing store or participating distribution partners. The flow that leverage microchip secure provisioning service is plugged into most of the e-commerce store of our industry there today. We try to make sure this technology, the secure element technology and secure provisioning service is available for the fragmented mass market. That's the name of the game in IoT. It's a lot of small, mid-sized project, not necessarily customers with project. We could have a small project, a large company that wants technology. Until now, they were limited by the MOQs. So that's what we believe we've changed the game there in terms of supply chain and technology availability. And we've done all of that by still keeping the technology fairly agnostic of the cloud provider, the public key infrastructure, the type of controller that sits next to it, the type of connectivity that sits next to it. If for more information, that's where you can go to microchip.com/trustflex. I won't have the time to show the page. We are at the top of the 30 minutes right now. But you go to this website and you'll see the several links actually that will point you to the Trust Platform Design Suite. And inside the Design Suite is where you're going to see the firmware IP protection use case and all of the use cases I mentioned in the previous slides there. And that's it for today. Megan, if you want to take it away, or if there are any questions.
Yeah, I just want to thank everyone for joining us today. We hope you found this session informative, and you can visit www.microchip.com/shields-up to view all upcoming sessions and watch past presentations on demand. Be sure to follow us on LinkedIn, Facebook, Twitter, Instagram, and YouTube for the latest news and updates. Thank you again for your time, and we hope to see you during our next sessions. Have a great rest of your day.